You'll find it there, and not some of the other earlier. The schedule has changed since that schedule, so we're taking a look.
What? This,
Oh, so this microphone on.
why am I getting the echoes? Oh, there's all these echoes.
Oh, but the doesn't.
You want to mute?
It is muted. Yeah, it's muted. I'm muted.
Yeah, I just powered on. We were missing the power strip, and now there's a second microphone active somewhere.
Does someone in here have the Zoom link open with the microphone on? You're off. It's not you. I can see your muted here.
Yeah. Aspen Physics doesn't have a mute.
Is the echo still? Yeah.
You still hear it?
Is there just a simple volume?
Oh, okay. All right. Oh, my speaker, I see. Okay.
I think that's it.
Thank you.
I will double check the front, but
I don't apologize. Okay, so. So we're happy to have Subir Sachdev from Harvard University. Someone who really doesn't need any introduction.
Okay, thank you, Daniel. Okay, all right, and you can hear me online also, I hope. All right, so thanks a lot for inviting me and organizing this wonderful conference. So I'll talk about topics related to things you heard about this morning, where you heard a lot about Kondo lattices and their application to heavy fermion compounds. And what I'll talk about is the application of related ideas to the cuprates. In particular, the fact that the cuprates have only a single band makes the problem, you would think, simpler, but actually in some ways a little much more subtle also. Okay. All right, so the central actor in the discussion I'm going to present is the Luttinger relation, which I have written here. So this is a relation obviously satisfied by free electrons, so they form a Fermi surface, and the volume enclosed by the Fermi surface equals the density of electrons modulo 2. And the theorem is that this particular volume is sort of a topological invariant and doesn't change if you turn on interactions as long as there is no phase transition. You can get modified Luttinger relations in phases of matter, we know today. And so that's not really ruled out by the old proofs because the proofs were ultimately perturbated about the free electron theory. Okay, so I'll begin with just a review of violations of the Luttinger relation in the Kondo lattice. This will be going over things that were talked about this morning, but perhaps a slightly different perspective. And then I'll talk about applying that some related ideas to the Hubbard model, which is what you need to do to understand the cuprates. So there's one very simple state that we know exists now, which didn't exist in Luttinger's time, which is the spin liquid. So I'm just showing you an example. This is some RVB state on the triangle lattice, say, yes? I think I know what that is. Is that better? Okay, great. Thank you. So an RVB state is some resonating valence bonds on a triangle lattice. So this is a state of matter that, whoops. Yeah, okay, that doesn't break any symmetries and has a density of 1 electron per size. So a density of 1 electron with the free electrons would give you a Fermi surface in the triangle lattice, say, but there is no Fermi surface here. So this is really the simplest example of a violation of a Luttinger relation. But you might not be very happy about it because it's not even a metal, so it seems kind of unfair to apply this to the system. But there's a simple way to form a metal just have another band, which I'll call the conduction band of C electrons, and call this band the F electrons. And now this system taken together has a density of 1 plus p, where p is the density of the C electrons. And so, but the Fermi surface size, which is just the C electrons, is p. So that's also slightly better violation. But the important point is that when you couple these two systems together, for example, via Kondo exchange, that you can establish quite reliably by a variety of methods that this Fermi surface size of size p is stable, that you can turn on JK over a finite range, and this Fermi surface size won't change. So now you have a coupled system of electrons. You could rewrite this part as a Hubbard model. So it's an electronic system. And this is explicitly, by anybody's definition, then a violation of the Luttinger relation. The price you have to pay to violate it is that there's topological order here in the spin liquid. And there's a remnant of the Luttinger arguments in the spin liquid, which I won't say much about, goes by the name of symmetry-enriched topological phases. And there's, in fact, a close relationship between the modern Oshikawa way of thinking about the Luttinger relation and symmetry-enriched topological phases in insulators. Okay, so then you can write down in this picture, in this Kondo lattice model, say, a simple wave function for this state, which we call FL star, and a closely related state that was discussed this morning is the OSMT, which is essentially closely related thing, obtained more from DMFT rather than, doesn't pay attention to topological order, which is really ultimately needed in the formal proofs of the stability. Yes?
Maybe very dumb question, but you would also have the violation of Luttinger theorem if the electrons were not topologically ordered, but just synthetically ordered.
No.
Because they would be localized, and it's still 1 plus p electrons.
Okay, so if you have magnetic order, then you increase the size of the unit cell, and the number of electrons per unit cell is a multiple of 2. So remember the mod 2. So the mod 2 disappears, and so there's no violation of Luttinger relation. The conventional Luttinger relation would apply if you broke translational symmetry. Ferromagnetically ordered, also there is no violation. Here I'm assuming spin symmetry. There are in fact 2 separate Luttinger relations for spin up and spin down, and they both work out correctly for ferromagnet. If you have spin ordering, then it's mod 1, not mod 2. I mean, if you have ferromagnetism. Okay, so these are all details, but that's an important point. If the spin liquid had magnetic order, then because of the doubling of the unit cell, at least, and the mod 2 in the Luttinger relation, there's no problem with the Luttinger. So you do need, anytime when you have a true violation of the Luttinger relation, as originally stated, you definitely need topological order. Okay. All right, so I was saying that there's a simple wave function you can write down for this phase, and it's, the way of presenting it, it's much simpler than the other phase. You just take a spin liquid of the F electrons and a free fermion slated determinant of the C, and that's pretty much it. Okay, so now if you turn up JK, then eventually there's a phase transition to another phase, which does obey the Luttinger theorem. And for a long time it was thought that that phase is the true phase, but it isn't. And this phase obeys the Luttinger relation because you count both the F and the C electrons. And now the wave function is somewhat different. You hybridize the 2 bands, and then you get a slated determinant of the hybridized bands, and then you can project that onto 1 fermion per site. And what the gauge theories of this, which I'll briefly mention, of this phase have shown is that this projection operation is not that drastic. We now understand what it does. And one of the things it doesn't do is change the size of the Fermi surface. It does make the quasi-particles much heavier, but does not change the size of the Fermi surface. Okay. So here's a little bit about the gauge theory. So in the Kondo lattice, there's a global U1 symmetry under which the electrons, the C band is charged, and there's a gauge symmetry associated with the projection into one F electron per site. And the FL star state, these two symmetries are really distinct to each other. If you apply the Luttinger argument to the gauge symmetry, you get some constraints on the spin liquid. If you apply that to the C electrons, you get the small Fermi surface size. Okay, that's also now quite simple to understand. But the subtle part, really, in this way of thinking, is how you get the heavy Fermi liquid state. So what's happened in the heavy Fermi liquid state is that this symmetry, this very large symmetry, is broken down due to the condensation of a Higgs boson. So there's a Higgs boson, which is just the hybridization operator between the two bands. And this breaks the symmetry to a diagonal symmetry. And once you break a symmetry, you don't have to worry about the Luttinger relation anymore. The condensation, that's why we don't have a Luttinger relation for bosons, or for a superfluid, because you've broken the U1 symmetry. But here, so therefore, you have to look at the symmetry that's unbroken. And a symmetry that's unbroken is a diagonal symmetry under which both F and C are charged. And that will give you a large Fermi surface because you have to count both F and C. And really all I want to use here is the fact that there's a very simple effective Hamiltonian you can use to work out the band structure of the heavy Fermi liquid state. And the variational parameter here is just this hybridization B, which is the condensate, the Higgs condensate. Okay. So, obviously I'm saying things that many of you know very well, and it goes back to beautiful early work of Pierce. And this whole approach has been extremely successful in describing the HFL phase. Okay. Well, I went backwards, sorry. So I just want to mention here this very recent experiment by James Analytis' group in cesium, cobalt, indium 5, where they have fairly convincing evidence of a phase transition in a regime where there is no magnetic border. Okay, so that's just an introduction and a review of things you heard about this morning in different formats. Let's now go to the Hubbard model. So the Hubbard model is a single band model which we want to describe the cuprates with. So what would you do? Well, first of all, if I just apply the usual arguments to this model, you should get, when you dope the system with p holes, or 1 minus p electrons, the size of the Fermi surface should be 1 plus p, in terms of holes, as long as you don't break any symmetry. There's simply no way around that in the usual Luttinger type approach. Okay, and this is sometimes called the vanilla theory, where you just take a slated determinant of electrons, and all you do is project out the doubly occupied sites. And the important point is that this projection only enhances the mass of the quasi-particles, but does not change the size of the Fermi surface. Sometimes it's called the Brinkman-Rice enhancement of the vanilla Fermi liquid. Okay, and this vanilla Fermi liquid, when I apply it to the cuprates, certainly works very well when you go to the overdope side. So here's some photoemission data showing you a large Fermi surface of size 1 plus p holes, or 1 minus p electrons, obeyed very accurately on the overdope side. All right, so my focus here is really not on this, but I want to now go to the underdope side. So on the underdope side, which is what you see in the photoemission, well, this is one very famous paper of ZX's group in an underdoped cuprate. That big Fermi surface has disappeared, and you have these features that are sometimes called Fermi arcs. But also very importantly, you have a gap in the antinodal region here. There's no excitations here, low energy excitations near the Fermi surface. Now, since then, of course, this has been looked at much more carefully. In particular, I want to focus on the high energy excitations here along the antinodes. So this is another famous paper by ZX Shen's group showing you these excitations in that regime. So what do we have here? So they're actually lowering the temperature, but at higher temperatures, before you enter the pseudo gap, you have this dispersion here, which, so as you go along this axis, you are moving along this axis over here. And this zero crossing here, which you see in the overdoped side and also at higher temperatures and underdoped side, that zero crossing there is not here, it's here. So that zero crossing are these 2 points here. Okay. So then when you lower the temperature, you ignore the green line, you get this dispersion here, which has got a gap-like feature. So this is the electron excitations below zero energy right here. So that's the pseudo gap right there. And this is not related to superconductivity. The green line is related to superconductivity in some way. And an important point here, which Patrick Lee has particularly emphasized, is that the maximum of this dispersion here, this gap, occurs at a different momentum than the Fermi surface point here. And so to explain that, Patrick Lee has postulated a pair density wave. I'm not going to use that approach. Okay. And I'll tell you how we think about this. Also, if you look on the antinodal side, on the nodal point, this here is a scan, I think, somewhere here through the nodes. And there you get a Fermi surface crossing. That's and there's hardly any difference between the overdoped and the underdoped side. They're pretty much the same. And in fact, that's an issue with the pair density wave model that gives you all kinds of bizarre structures near the nodal regime. Okay. All right, I'm not really going to explain this data. This is ADMR data that has also been mentioned by Brad Ramshaw and Louis Taillefer, showing some evidence for pocket-like Fermi surfaces in the underdoped regime. Okay, so what I'd like to talk about, to finally come to our recent work, is a model for this pseudogap metal. And my model for this metal will be this FL star-like state. But the big question really is, how do you get that state in a one-band model in some reasonable way that you can do some calculations? And I'm not going to claim that this kind of, so this requires some kind of topological order of fractionalization. I don't believe that order, there's a lot of evidence, in fact, it doesn't survive as you go to low temperature. So there's some very complicated crossover to confinement, on which there have also been many papers, but I won't discuss that. So I'm just going to sit over here and postulate that in some other universe, perhaps this metallic state could be stable down to zero temperature and see how far that gets us. So think of it as a quantum phase in its own right, rather than fluctuating of something else. Okay. And there's been a lot of work on this rough idea. I would say the first paper which had this kind of idea is a paper of Wen and Lee going back to '96. And there have been many other papers, including many by my group. I'm not going to talk about any of these, because in the end, all of these never give you a workable way to compute something you can compare with experiments. And why is that? Well, here's sort of the general route many of these papers have followed. So the idea is you go to fractionalize, you got to have spin charge separation. So you take your electron and write it in terms of a spin on and a hold on. You can choose your statistics as you wish. And you do this to every electron. So that gives you some very exotic system, which has no electrons left. But then you say, well, the hopping is actually very attractive between holons and spin-ons. So maybe every holon binds a spin-on, and you get an electron-like state, which is of density P. And these bound states form a little pocket. That, in a quick summary, is the summary of all those papers in some one way or the other. And the argument is that this whole, this bound state formation must happen because T is much bigger than J. Okay, well, fine. I don't argue with any of these steps. In fact, I've written papers arguing for these steps. It's all right, but it's still very extremely cumbersome. And the lesson we have learned from the Kondo lattice is that we never did this in the Kondo lattice. When we analyzed the Kondo lattice, the conduction electrons just remain conduction electrons. It was the spins that we fractionalized. So what do we have to fractionalize here? We have to fractionalize the paramagnon. So now I'll tell you what we do. So this is the work. The main idea actually was due to Xiaohui Zhang a couple of years ago, and we've been working on it in many different applications of it. I'm going to talk about recent work with Alex Nikolenko and Maria Tikhanovskaya, two students at Harvard, and Eric is a student at Chicago with Dirk. Okay, so we start with the Hubbard model, one band Hubbard model, and we rewrite the Hubbard interaction as something spin squared times a constant. And then you do the Hubbard-Straton-based transformation, and when you get this field phi, which couples to the spin density of the electrons. So this is a very well-trodden path, going back to theories of helium-3 for ferromagnetism, and various people, Scalapino, Pines, Chibukov, Shmalian, many people have used this kind of theory of a fluctuating paramagnon coupled to a Fermi surface as a theory of spin fluctuations in the cuprates. All right, so that's all fine. I'm happy to use it, but this, if you use it to all orders, you always get, when you don't break symmetry, you get a large Fermi surface. Okay, so what I want to do is to rewrite that theory, first of all, in Hamiltonian form. So I'll give the rotors this phi field some kinetic energy, and I'll restrict it to have unit length. These are all for convenience. You don't have to, the specific form won't matter much at all. So then you have, here's your two-dimensional lattice of electrons of density 1 plus p. And then you have a rotor on each side, which I think of as a blue particle that's moving on the sphere. Okay, so there's a particle which is just the, its position as the spin density is the spin operator, this phi operator, and it has some angular momentum, which we call L. So this is the part that we imagine we get by integrating out some very high energy degrees of freedom. All right. So if I just diagonalize these, look at the spectrum of this particle on each sphere, it has the exact same spectrum as a particle moving on a sphere, which is a bunch of angular momentum eigenstates with some eigenvalues GL into L plus 1 and degeneracy L equals 0, 1, 2. So the important point to keep in mind is that it doesn't have definite angular momentum, but it has integer angular momentum, just like an electron in a hydrogen atom. So the main assumption is that two lowest lying states of this paramagnon on each side are L equals 0 and 1. And I throw out all the rest. So I just want to keep the two states. I can keep more. It just makes life more complicated, but let's keep the simplest thing. And now I think of this singlet and this triplet as the states of two spins. So this is now the fractionalization. I'm going to replace each rotor by two spins. Okay, so now if I take J perp to be large, the ground state of these two spins is a singlet, and it has a triplet excited states. And so these two spins, and that's the key point, you need two spins to represent this rotor. Okay, so here's now my model, which we have the physical, it's really a theory of the Hubbard model. I've just done some canonical transformations, and I'll undo them in a minute. So here's the physical electrons, and then I have these two spins, two layers of spins. Each sits on a square lattice with some coupling J perp between them. They're not symmetric. There's no reflection symmetry. And that's related to this fact that this phi operator is really the difference of the two spins. So it turns out one of the spins is coupled ferromagnetically to that layer, this one actually, and this is coupled antiferromagnetically. So since ferromagnetic couplings are not important, we can just throw it out and we keep only the antiferromagnetic coupling, which is why I'm calling it J Kondo. Okay, and you can also put in interactions between these spins if you want. That's J1 and J2. So now I can go back to the Hubbard model from this model just by doing a Schrieffer-Wolff transformation and getting in 1 over J perp. And when you do that, you get back the Hubbard model with some additional interactions, and use the expressions. Okay. Now, I often get asked, well, how can I compute these quantities? Well, it's not an easy task, but who said the Hubbard model? It's very similar to the Hubbard model itself. The Hubbard model is not God-given. It's not really the real model. Computing U in the Hubbard model is a very complicated business. Involves a lot of DMFT and other works to figure out what's the value of U, and there are similar difficulties here. Anyway, so now I have this model, and I'm going to look at its phases. So at large J perp, I have a very simple phase where these spins log into singlets. And you can get a singlet triplet excitation here, and that's exactly the paramagnon. So if I start from this state and I do perturbation theory in JK, I will come back to the Fines, Schmalian, Chubukov, Scalapino theory. You'll just rederive it, basically get it, which only gives you a large Fermi surface because you've got these conduction electrons coupled to the paramagnon. Okay, and here's a very simple wave function. All right, so how do you get a more exotic state? Well, what you do, obviously, is you do to the first 2 layers what you did to the Kondo lattice. So you take the conduction electrons here and the first layer of spins, and they form the heavy Fermi liquid state, just like in the Kondo lattice. So now what's the density size of the Fermi surface? So these 2 layers have a density of 2 plus P, because you have 1 plus P here and 1 here in terms of holes, but everything is mod 2. So this actually, here the heavy Fermi liquid state has a small Fermi surface. And finally, so you have violated Luttinger's theorem, it seems. And remember, I told you that must mean there must be a spin liquid somewhere, and indeed, here it is. There is a spin liquid sitting here, and this could be almost any spin liquid that people have understood. Z2 spin liquid, Carl spin liquid, Dirac spin liquid, spin on. It's all possible. And now I can even write down a very simple wave function. In fact, this is for the case that there's a spin-on Fermi surface here. So what I do is I form a slated determinant of C and psi, the top 2 layers, just like I did in the heavy Fermi liquid. And then I form a slated determinant of psi 2. And then I project, and this is, of course, the hard part, project onto rung singlets of psi 1, psi 2. So now you can see from this wave function, which we've never had before for a single band FL star state, it's a wave function on the physical electrons. Everything out here is projected out. Now, how you do the projection is a bit complicated. I won't go into it. Now you get an SU2 gauge theory, and it's more, but anyway, so there's a way of understanding how this works. But fortunately, you don't have to really work very hard because you just do the same kind of mean field theory you did for the heavy Fermi liquid for the Kondo lattice. It's just, you hope that that works. So that's what we're going to try. So we'll just take the top 2 layers and even ignore the bottom spin liquid for now. And so you have the physical electron, you have the first layer, and then you have the hybridization between them. And this actually completely breaks these SU2 gauge groups. The only thing that's left over is the SU2 on the second layer, on the bottom layer, which I'll say a little bit about maybe. Okay, so here's what we're going to use to fit the data. The Tij we know. The T1 Ij are our free parameters. And the phi determines the pseudo gap, which we also know. Okay, so for example, here, the red line is the Tij Fermi surface. The dashed line is the T1 Ij Fermi surface. And the blue line is what you get when you hybridize them with phi. And this pretty much fixes everything. And you get these arc-like structures in the nodal region. But now let's just look at what happens to the dispersion over here. And the whole thing is, we have fitting parameters, but it's really over-constrained. So we want to look at what happens here. So here's what you've got. So here the red line is the T1 dispersion. the dashed black line is the T dispersion, excuse me. The dashed black line is the T1 dispersion. And notice it crosses 0 at a different point than this one. And that's because the density of the two is very different. The density of the second layer is 1, and the density of the C layer is 1 minus P. And it also is hole-like dispersion, which is also what we used in the previous one. And then you put them together and you get this gap dispersion in the antinode. On the other hand, if you look near the nodal region, this is the red line is what you get, which is actually very similar to what you would get on the overdoped side without any pseudo gap opening up. All right, so here's a comparison between this data I showed you here. This is the blue line here, and the prediction on the antinodal side, and this is the nodal dispersion. And also, this doesn't vary very much with doping at all, whereas this, as in other models, that's not the case. Okay, so we get, it seems like all the basic features. Okay, so how am I doing on time? Okay, great. All right, perfect. So the one thing I haven't talked about now is the second layer. So that has to be there just because of the fact that you violated Luttinger's theorem. And so we'll just treat it perturbatively. So we imagine we understand spin liquid physics, which today perhaps is not an understatement. So we understand this and we know something about various spin liquids. So we can compute this chi-SL. And we just perturbatively couple it to these two electrons, these are the first two layers. Remember, I told you in the first two layers, it's just like the heavy Fermi liquid. There are no singular gauge fluctuations. All the singular stuff has been pushed down to the bottom layer, which we can then treat. We've understood a lot how to treat that. So you can just look at. So we just looked at this first correction, and this changes the line shape. So here are, in fact, in this case, we took an SYK spin liquid because it's just took spin correlation and momentum independent. It's much harder to compute it in a momentum dependent spin liquid. We haven't done the MDC in that case yet, but it's not so sensitive to those details. I can't tell you what the spin liquid is, but if you take some reasonable model for the spin for this chi spin liquid, you get the line shapes, both the MDC and the EDCs, and they agree reasonably well. Okay, with this subsequent later paper by ZX's group, which is also referred to this morning. Okay, so that's the end of the main part of my talk. So I first reviewed results on FL star phase in the Kondo lattice, and I presented a new theory for FL star phase for the pseudogap metal phase of the cuprates. And the bottom line, it can be summarized in a couple of sentences. First of all, don't fractionalize the electron, fractionalize the paramagnon. So they fractionalize the paramagnon in two sets of spins, one of which hybridizes with the conduction electron, just like in the Kondo lattice, and the other forms a spinel liquid. And that gives you a completely controlled theory of an FL star phase with an explicit wave function. Yeah. Okay. All right. So I had this is one So one way to figure out what's a good spin liquid, so I can't resist mentioning this, is to look at the J1, J2 model, just the insulator, because you can just look at the bottom layer is insulating. And there's some recent evidence in numerics for very interesting gapless Z2 spin liquid phase of the type Senthil and Fisher first discussed. And so we've done a lot of work on this kind of phase and also applied it to this particular model in this paper with Henry and Alex. Okay. Yeah, I have some bunch on stuff on quantum criticality, but I think I'll stop. If there's questions on quantum criticality, happy to address it, but that is of course much less understood. The one thing I want to emphasize, if you're in the pseudo gap phase, things seem in very good control. The transition from FL star to FL is still a work in progress. Yeah, okay, thank you.
So the liquid dispersion that you and the T1 hopping,
Yeah,
that is kind of vector. Right?
it's what?
The T1 is there can be many different choices.
Yeah, it works best if you take it to have the opposite sign. It's hole-like dispersion. And you can also kind of understand that because it's really describing a correlation hole of the electrons at the top layer. Yeah, so the T1 has the opposite sign from the T. From T.
It could have second neighbor, third neighbor.
Yeah, we take those. We do take that. So to get, I mean, there are fitting parameters, and the T, it's where did it go? Yeah, oops. Yeah, so this we take, we take first, second, and third neighbor hopping here, and also first, second, and third neighbor hopping there, and 1, 5. So if you wish, there are 4 free parameters, the T1s here and the 5s. Yep. The chemical potential you're not free to fix. You fix that, it's important. You fix that to have exactly density 1 on the second layer. And that's kind of, in this paper of Chen et al., they had various models, or no, the earlier paper of Hay et al. They had a huge long supplement of SDW and various other ordering parameters. There's a difference there because there, if you take an SDW model, you end up having your dispersion of the second band is you're not free to choose it, and it leads to all kinds of difficulties. They can't do as well as we can.
Is it talk about the second layer getting out of the beam at low temperature somehow?
Well, it's more complicated than that. Yeah, I can't elaborate on it because I would say on the whole, it's not well understood. We can talk about a deconfined critical point in between and its structure, but exactly how that deconfined state goes from, so basically what you get at the critical point is you have a Fermi surface here, and the hybridization goes to 0. Let's just take the theory of the pseudo gap and send the hybridization to 0. That's the main. And then you liberate the gauge fields on this second layer. And so you have a Fermi surface of psi 1 also appearing. And then you have a spin liquid of psi 2. And so that you can write down a deconfined critical state. It could even be a phase. But then how that phase confines into this state, yeah, well, we don't know. We don't have a description of that under any control.
What's the size scale of the gap in this theory in terms of the original Hubbard model P and U, and maybe this is related to your quantum criticality? What happens?
Well, I mean, we just, we do look at the experiment. So here you can see the, oops, sorry, here. So this is the pseudo gap phi right there. So it's about 30 MeV. So that's a parameter we just take from this data. We put 30 MeV.
But you don't calculate that explicitly.
No. I mean, we'd love to. I mean, those are much harder things. Yeah.
If I understood correctly, you introduced the LS squared term by hand,
Yeah.
you truncate the plot, but you still get very much the J model at the end. I'm very surprised that it looks so nice at the end.
Well, it's more than it's 2 layers. I mean, really the important thing, you get a condo lattice model for the top, but you also have the second layer. There have been various people adding layers before. I think in some ways you could interpret some of the YRZ theories in that way, but they don't add the second layer. I mean, and that's inconsistent. You can only add 2 layers because then all anomalies, the important thing about what you add, you can only add trivial things. So here, this bilayer system has a trivial ground state, which is this one. That's why it's okay to add it. You can add more layers, but as long as they come in pairs, because then as long as you can always add something trivial. That's just another language for the Hubbard-Stranovic transformation. That's what the Hubbard-Stranovic transformation does. It adds trivial things, which can then acquire some new dynamics. But we are very careful not to acquire anything non-trivial when we add the L squared.
Yeah, I was wondering whether there's any obvious relation between the model and the materials. So can you relate one of the layers to something or the other layer to something?
this is a theory of one layer. That's really, yeah, no, I mean, so if I look at this wave function here, this wave function here, it's a function only of the electron coordinates on this layer. It doesn't depend on anything else. It's just you could think of it like in the tensor. I mean, it's sort of like the tensor network picture, right? You tensor network, you have the physical coordinates, and then you add some additional things which you do a matrix product over. That's really all we're doing. We're adding these two layers, but in a way that's, that we know how to work with using field theory and other tricks. But in the end, when you do this projection, there's no dependence on the left-hand side. This state is a function only of the coordinates in this physical layer. Okay, and we know how to do that with gauge theories in higher dimensions. I mean, there's some similarity to ideas of tensor networks, but tensor networks, they don't have fermions to begin with. They can't even get a Fermi surface, and everything has to be done numerically. Here we have some ideas on how to proceed with this kind of ancilla degrees of freedom.
One last question. Do you think any signatures of the spin liquid part have been already observed in experiments?
Well, I mean, I wouldn't say, well, of course, you're right. So to conclusively settle this model, eventually the dream is that you will see, first of all, you see these top two layers, and that has its own spin excitations, but you'll see some additional spin excitations which are associated with the bottom layer. But this is not as if we're adding degrees of freedom. They're really required at low energies. And this calculation here, I wouldn't say, I didn't beat my drum about it too much because, there's a lot of free parameters here. But in this calculation, that is what we were trying to do. Here, we were trying to understand the full line shape. And to understand the line shape, we have to then look at some low energy scattering. And we said, well, let's assume the low energy scattering is from the spin liquid. And we get reasonable fits. So let's just leave it at that. But this is by no means conclusive.
One more question.
Sure, no problem at all. Yeah. So you can go back to the paramag, and we have done that. We even have deconfined critical points and so on. That's the second paper with Yahui. But you just go back to this state, for example, and I said, and then you have a singlet triplet excitation. That's the phi particle, and you can condense it, and you can get antiferromagnetism. You can get all of the work that's been done by Chivokov and friends who can reproduce, or not reproduce. There's a way to go that way if you wanted to. But now when you fractionalize that phi, then you can get something different. Yeah.
Exactly the way she said. I should not have lost faith.
Oh, I'm sorry.
I actually do need a pointer. Mine exploded.
You have to install
You can use the mouse.
I can use a mouse.
mouse and all like people to see this.
I have my own wireless presenter, but I pulled it out of my bag after 2 years of no use and the battery had exploded. So I will need to borrow one. Is there a pointer somewhere? Or I guess I could just use the mouse. All right. Well, I think I have enough battery.
There's one here. I don't know. I think it may reach around. It's right on the phone.
Okay. Okay. Yeah, and then I need to push this, right? I'd like to say that it's a privilege to be with all of you in person. This is my first in-person meeting in 2 years. 74553. Recorded, fine. Sorry. And then you probably want. So that gets it through this. Okay, share.
So you haven't been, she's
I see.
enabling you as a co-host.
I
right?
see, okay. Okay, I'll use the mouse. I can probably use this thing, right? This?
Yeah, perfect.
Okay, I'm going to talk about a new mode that we've discovered.
I'll let you go ahead.
Oh, I'm Peter Abbamonte from the University of Illinois. Unmute to start speaking. Do I need to unmute myself? Okay. So I'm going to talk about a new excitation that we've seen using electron energy loss spectroscopy. We've spent probably a good 18 months or more trying to understand what it is. And I think what it is an instance of a particle that was proposed by David Pines in the 1950s called a demon. So I'm going to show the experimental results and present arguments for why we think that's what it is. I'll also explain what this mode is. I have 30 minutes? 30 minutes plus. Oh, I can take off my mask. Okay. All right, so in my group, today we've seen a lot of susceptibilities in various talks. In my group, we've spent the last 9 years trying to measure this one, the charge response at finite wave vector and milli eV energy loss. Quantity is a Green's function. It describes how excitations propagate in a material. Its imaginary part you can think of as like the spectral function for charged bosons in the system. It's of interest for many reasons. I don't need to list them all for you. I'm sure you're all fully invested in this kind of thing. So I'm going to just jump right into the experiments. So the technique is called surface electron energy loss. What's new is we've put a lot of energy into making it momentum resolved. So we call it MEALS. It measures the density response of a surface. And this is basically what happens. You shoot an electron at the surface and it scatters a collective mode. The energy resolution of this technique is a few milli eV, and the momentum resolution is a few hundredths of an inverse angstrom. So the kinematics are similar to angle resolved photoemission or neutron scattering in the resolutions. So the differential scattering cross section is some matrix elements times S of Q and omega, which is the surface density correlation function. So the disadvantage of this technique is that it is a surface probe like photoemission or STM. The advantage is it actually measures the response function that we need. So this density response is actually a Bose factor times chi double prime of the surface. So there's a conversation to be had over what response function this is. But for example, if the system is Q independent, if the response is Q independent, you can show this is just the imaginary part of 1 over 1 plus epsilon. So it's almost imaginary part of 1 over epsilon. And important, epsilon is the bulk dielectric function. So this is not, it's not really a surface probe in the same way as STM. It's more of a bulk probe of a semi-infinite system where you have to consider the fact that there's an interface that you have to interact with to get data. Okay, so we've written quite a few papers on strange metals, and I'm not going to talk about strange metals much, but the fruit fly of strange metals for spectroscopies is BISCO. In this material, if you look at the Brouillon zone, what we've shown is that in a small circle near the gamma point with a radius of about 1/8 of a Brouillon zone, what you have is a plasmon. A plasma frequency is around 1 eV. You can see this thing in optics too. And anywhere else in momentum space you look, there's a continuum. And the continuum is constant in frequency in the strange metal phase. It's also constant in momentum. modulo a q squared factor that's needed to satisfy the F sum rule. And the interesting thing about the continuum is it looks a lot like these old conjectures about the marginal Fermi liquid from the late 1980s, early 1990s, in the sense that there is a large region where the susceptibility is constant and the thing is basically momentum independent. So we've already heard today discussion related to what could be the microscopic origin of this thing, one being this SYK model, which gives you a frequency independent susceptibility in the imaginary part. So that's just a little bit of background. What I'm going to talk about today is strontium ruthenate. So this is a lot like the cuprate materials. The difference being, so at low temperature, it turns into some kind of exotic superconductor that we now know is not triplet P wave, or maybe it is. Can have a discussion about that too. For this talk, what I'm going to be interested in is the fact that it has a Fermi liquid to strange metal crossover. At low temperature, the resistivity is T squared. But if you go to above room temperature, eventually it becomes T linear and it surpasses the Mott-Joffe-Rego limit and becomes a bad metal. So this is an interesting material that sort of turns from a Fermi liquid into a strange metal as a function of energy scale, either through temperature or maybe the speed of the measurement or so on. So it's an opportunity to kind of look at something that bridges conventional physics to strange metal physics like we've seen in BISCO. So if you look at high energy, this system looks a lot like a strange metal. At very low momentum, there is a plasmon. It's very broad. The frequency is a little higher than it is in the cuprates. It's about 1.2 EV. It's very broad. Some of that is because it's measured at finite wave vector. It's sharper if you measure it in optics. But what happens as a function of momentum is it evolves into a frequency independent continuum. And this has all the same scaling properties as the continuum in BISCO. It's essentially momentum independent over most of reciprocal space. And it's frequency independent up to some cutoff beyond which it just decays like 1 over omega squared. People have asked us how we know this is not a surface effect. So we've actually done transmission eels measurements now, not only in both this material and in BISCO. So that's a bulk probe, and we can show that you get quantitative agreement. That's actually what's in this plot with transmission measurements. So it's a bulk effect, and it's highly reproducible. We've seen it in dozens of different materials, multiple different grad students with different PhD theses, different postdocs. So it's highly, highly reproducible. So it looks like if you look at high energy scales of EV, strontium ruthenate does in fact look like a strange metal. What I'm going to talk about today is low energy. So if you go down into the low energy regime, yes.
So just as a benchmark, you see something like this in copper or copper?
Copper has a nice plasmon at about 16 electron volts. It's pretty sharp at low frequency. And as you increase momentum, it disperses like Q squared and it gets broader because of Landau damping. And the spectral weight in it as a function of Q is, if you do the F sum rule, it satisfies the F sum rule really nice, goes like Q squared. That excitation is so high energy, we actually can't measure it with this technique because our beam energy is only 20 to 50 EV. So to measure something with energy loss of 16 EV is sort of untenable. But yeah, so we've studied doped semiconductors. Actually, bismuth selenide recently, if you take that, that's prone to acquire selenium vacancies, and so it gets bulk conduction. That has a nice plasmon at about 20 millieV, depends on, and if you heat it up, the plasma frequency shifts around. And it seems to satisfy, then the frequency of the plasmon is what you would expect based on 4 pi Ne squared over m star, where m star is the known effective mass from the bands. It works quite well. Yeah, so every time I show BISCO, everybody says, have you looked at a conventional material? Unfortunately, if I show a conventional material, they say, why aren't you measuring BISCO? But then you only have half an hour to give a talk. So I can't show all of it, but I have data I can show you that it does work. And it shows data that are consistent with optics and other probes of the cuprates too. Okay, so back to strontium ruthenate. At low energy, there's a mode down there that we didn't expect. So this axis is millieV, so this is 0 to 80 MeV, and this is momentum in reciprocal lattice units. So it's at a quite small momentum scale, something like 0.02 to 0.08 reciprocal lattice units. A reciprocal lattice unit is just take the inverse of it, and that's the wavelength in lattice parameters. So it's so we saw this gapless mode. We didn't know what it was, but gapless modes are a sign of a Fermi liquid. So this is what you expect is a collective excitations that propagate well, response functions that are Q dependent. So we wrote a paper and submitted it and said at low energy, it's clearly a Fermi liquid. There's a Fermi liquid-like mode, and then there's a crossover to high energy where it acts like a strange metal, which is sort of what you would expect based on the transport. And we got a lot of criticism from the referees for not saying what this mode is. And there was a reason I didn't say what it was, which is I didn't know. But sometimes you just have to be an experimentalist and say, we saw this and we don't know what it is. But okay, so we've had some time to reflect. And so I'm going to tell you that I think it's a demon. So there are kind of 4 things that you could go through to guess what this mode might be. The first guess you might think, is it an acoustic phonon? Acoustic phonons are gapless. Oh, I probably should have said that. The most important feature of this mode is it's gapless. If you go to 0 momentum, the frequency goes to 0. And the dispersion is quite linear, though it seems to cross over to a Q squared at low energy. And that Q squared is real. We spent some time investigating whether that's something that's due to a finite resolution, and that's a real Q squared down there. So what could it be? So you might guess that it could be an acoustic phonon, but if you look at the velocity of the thing, it's around 0.5 eV angstrom. The sound velocity, which is the velocity of the acoustic phonons, is about a factor of 100 times smaller than that. So this thing cannot be a lattice excitation. It's way too fast. It's got to be something electronic. Another thing one might guess is that it's a surface plasmon. Surface plasmons are gapless. If you open Ashcroft and Merman, they show you that surface plasmons always go to 0 frequency at 0 momentum. In this case, the velocity is far too low. So the reason surface plasmons are gapless is at small momentum, they become polariton-like and they mix with a photon. And actually the gaplessness is because a photon is gapless. It turns out that regime happens at such low momentum, it can't be measured with massive particles. So if you look at surface plasmons and things like Eel's techniques, where they all show up at what is called the Ricci frequency, which in a simple Drude metal is omega p divided by the square root of 2, though what it really is at the point where the real part of the dielectric function crosses -1. That point has been measured in strontium ruthenate by Dirk van der Marel's group, and it happens at 1.3 eV. So it is not anywhere near in the energy scale of anything that could explain what this method is. It turns out strontium ruthenate also has a surface state. Surface states have been known to create gapless collective modes on surfaces just because a conventional plasmon in 2 dimensions is gapless. But we took measures, turns out not deliberately by accident, but we took them nevertheless. And it turns out if you fully passivate the surface of strontium ruthenate with carbon monoxide, which is in every ultra-high vacuum system, all the surface bonds get terminated and the surface states go away, and you get essentially what's the bulk Fermi surface. This is actually highly studied by STM and ARPA's groups, and we expose the system to at least 0.5 Langmuir of CO, which is well orders of magnitude more than is needed to passivate the surface state. So there aren't really any conventional explanations for what this mode could be. So what I'm going to argue is that it actually might be a demon. So what's a demon? Okay, so if you go back in time, long before most of us were born, there was this paper by David Pines published in the Canadian Journal of Physics in 1956. And obviously he was interested in things like plasmons and Fermi liquids. And what this paper shows is that if you have a system of 2 different charge carriers, let's say light electrons and heavy electrons, this could happen in a plasma, it could happen in a material with 2 different Fermi surfaces, then what you get are 2 plasmons. And if the conditions are right, one of those plasmons can end up at 0 frequency. So the way he considered it is there are each of these 2 baths of carriers would independently generate a plasmon. And if one of the baths is very light, the other one is very heavy, those 2 plasma frequencies will be very different. And so he called them capital omega, lower omega p. And what happens is you get 2 modes. One of them sits up at the sum of the 2 frequencies, and the other one ends up sitting at low frequency, and this really isn't moving fast, but it ends up being gapless, and it has a velocity s that's actually bounded by the Fermi velocities of the 2 different submassive carriers. So it's not a rigorous numerical calculation. It was sort of a heuristic argument, but he argued that any material where you have more than one species of charge carrier, such an excitation could exist. Now, so this is the key feature that got us interested in this, is the fact that it's gapless, okay? And in fact, the dispersion should be linear, which our mode is over most of its momentum range. The other feature of a demon that's really important is that it is neutral. So as you know, the normal metals screen charge, and this epsilon has to be finite and diverges at zero frequency. And epsilon is related to pi, the polarization, which is determined by the compressibility sum rule to be constant in a metal at at zero frequency in the low momentum limit. This is the compressibility sum rule. Because of this, the susceptibility in a normal metal has to go like Q squared at low frequency or at low momentum. And that in the normal metal, and I'm being somewhat mechanical here, is accomplished by the plasmon. And you can see it in copper, you can see it in graphite. What you see if you just do a measurement is there's a plasmon at finite frequency that's determined by 4 pi Ne squared over m star square root. And if you do the F sum rule, the spectral weight in that thing is required by the F sum rule to go like Q squared. The consequence, then that matches up with this pi that it forces the thing to be a metal. I'm being a little bit mechanical because I'm not a theorist. So, but this is what happens in a metal. So the compressibility sum rule and the finite conductivity and the plasma frequency and the F sum rule all sort of work together in a way that makes sense. A demon is different. A demon is actually neutral. And the reason it's gapless is because of this. You know, a plasmon, if I move the charge, there's a long-range Coulomb interaction that has to occur, that is always present, that puts the thing up at finite frequency. Okay, in a demon, it's made of two different charge carriers. The demon mode is where the two submassive carriers actually flow out of phase. So if I displace the demon coordinate, if you like, it doesn't build up any charge on the boundaries, and so the thing stays at zero frequency. That also means that in the long wavelength limit, a demon cannot screen. Can only screen at finite wave vector, which means that in the limit, the Q goes to 0 and omega equals 0. For a demon, epsilon has to be equal to 1, which means that the polarizability, the pi, has to go like something faster than Q squared. It has to be Q to the 2 plus alpha, where alpha is greater than 0. And that implies that chi has to do the same thing, okay? So actually, there's two ways to assess if an excitation is a demon. One is to look at whether it's gapless or not, and the other one is to see if it violates the F sum rule. So I'm getting ahead of myself, but a demon, its existence, it necessarily breaks low energy sum rules. You can't define a partial sum rule for a demon at low frequency the way you can for a plasmon and a doped semiconductor. And the reason is because it owes its existence to the presence of a high energy plasmon. If I have two baths of carriers, light ones and heavy ones, this is the way Pines thought of it. The light ones move so fast that they screen the Coulomb interaction between the heavy electrons. Those effectively become neutral, and then the collective mode of those at zero frequency, because it's like a collective mode of neutral particles. So the consequence of that is that the demon can't live without some conventional high energy plasmon that's screening all the charge away, which is the thing that allows the thing to be neutral. So this is the first time I've given a talk in public in 2 years, so maybe I'm being a little bit confused. But the point is, a demon has to violate the F sum rule because it can't exist independent of some high energy degrees of freedom. There has to be some UV IR mixing in the problem. Okay, so I think my watch stopped. How much time do I have? Quite a bit of time, right? 12 minutes, good. Okay, so strontium ruthenate. All right, so strontium ruthenate has 3 Fermi surfaces, not 2, and they owe their existence to these 3 different ruthenium T2G bands. So it's a candidate, I would call it a candidate demon material. It's not obvious it would necessarily have a demon. To know if it, for one thing, it has another band hanging around that could interfere, or maybe it could even create 2 demons, I don't know. But to know if strontium ruthenate has a demon, you have to do a microscopic calculation, which Pines never did. So he made some heuristic arguments that a demon should have such properties, but to know if a particular material is going to do it, you have to really calculate it. So this was done by Edwin Huang, who's sitting right there. Basically what he did is he took the physical, this is all Fermi liquid physics, so you can compute anything you want. So he took the physical band structure of strontium ruthenate, which there's a tight binding parameterization from Sergei Borisenko's group. So this is all parameterized well. And then he computed the Lindhard function, which is just a simple irreducible bubble. And then you can compute chi, the susceptibility that's actually measured in an experiment in RPA. RPA means this chi 0 is the Lindhard chi, not the one with all the many body interactions and things in it. So if you do that, you see some things that make lots of sense. For one thing, you see a high energy plasmon, which we see in strontium ruthenate as well. In ours, we see it at 1.2 eV. In the RPA, using no adjustable parameters at all, by the way. All that's used are the known band dispersions, the known background dielectric constant, which I think is 2.5 or forget exactly. And you just execute the calculation. And the first thing you see is there's a plasmon. And it sits at an energy that's not too far away from the experimentally observed one. Key difference is it's extremely sharp in RPA, whereas in the experiment, it's broader by 2 or 3 orders of magnitude from this. But okay, it shows that the mode exists and it has the right energy scale. So that's good. So now the question is there a gapless mode? If a demon is expected, there should be another mode down at low frequency. So if you look down there, you don't see one. So this is by the way, this is a color map. This is momentum on the horizontal axis, frequency on the vertical. The color scale is the imaginary part of chi. And chi goes like q squared for a conventional plasmon. So what's plotted here is chi double prime times 1 over q squared. So you can see the intensity goes to a constant here, which means that the sum rule is also being satisfied. If you look at low frequency, actually, well, nothing jumps out at you. You don't really see anything there. But wait just a second. You have to look really close. If you look really close, there's a mode there. And its dispersion is linear. But it seems to vanish as q goes to 0 in the calculation. Now, why is that? The reason is because this is chi double prime divided by q squared. But if it's a demon, its spectral weight has to go faster than q squared because it's neutral. So if you take it and you multiply by 1 over q to the 4th, its intensity goes to a constant. So what you can see is that there is a gapless mode in strontium ruthenate in RPA, and it seems to be a demon in the sense that it doesn't satisfy the F sum rule by itself. It goes faster than that, which would mean if this excitation were the only thing in the problem, if you calculated epsilon, it would be 1, because it wouldn't be able to screen, at least in the long wavelength limit. Okay, so if you compare that to the experiment, this is the current figure, which obviously we need to improve a little bit before we can publish it. But on the horizontal, again, is momentum in reciprocal lattice units. In the vertical is energy in milli eV. So this now has error bars both in the energy and the momentum direction. By the way, this is just an optical phonon. Okay, so that is a well-known mode that you can see with IR. And what you can see is that the velocity of the mode in RPA without any adjustable parameters is within 5% of the velocity seen in the experiment. So it really looks like it's the same mode. Now there's a funny issue of q squared down here that maybe we could talk about at the coffee break. But I've never seen such good quantitative agreement between a simple RPA calculation and an actual experiment. Okay, so are you lost?
Does the RPA include the demon or not?
The RPA, well, yes. Well, what do you mean include? You don't have to put it in by hand. You simply put the bands in and do RPA, and the demon will come out if it wants to. Does that make sense? But it's not required that a demon could exist. I mean, I could create a multiband metal that didn't have a demon for whatever incidental reasons. But strontium ruthenate should have one, if you believe RPA, which I don't, at least until this. But it clearly completely fails for this high energy mode, by the way. So if you look at the strange metal physics, it utterly dismally fails to predict the experiment at that kind of energy scale. But in the low energy regime, it seems to work. Yeah.
These have to be separate bands with their own dynamics.
Yeah, they should, if you believe Pine's papers, they should have different Fermi velocities. So that one you could call a fast one and the other one a slow one, so that one can screen the other. Yeah.
So do you have an idea of which two of the three bands are important?
Yes, it's the beta band and the gamma band. So, okay, let me just, I was even thinking of skipping this, but let me do it really quick. So the other thing that Edwin did is he figured out a way to resolve which bands are participating. So RPA, you just get chi, but you can be a little more subtle and compute a partial chi. So chi represents how the system responds if you drive it with some potential or something that couples to charge. But it's possible to do a band resolved chi and ask, how does the charge in the system respond if I drive it with the potential that couples only to one of the bands? So I could somehow invent a fictitious driver that just drives the beta band and ask, how does the gamma band and the alpha band respond due to that? And that allows one to define some partial susceptibilities. And what they look like is quite compelling. What you can show is that for the in phase, so if you drive if you drive the gamma band and look at the gamma response, it's quite, it has a positive sign, but if you look at what happens to the beta band, if you drive the gamma bands, it has the opposite sign. So what it means is that so a demon basically is a thing where electrons in one band oscillate out of phase with electrons in another band. So if I drive one of them, I can look at the sign of the response of the other one and ascertain whether it's in phase or out of phase. So as you can see, if I drive the gamma band, then the gamma band responds in the normal way because that's the one I'm driving. But if I drive the gamma band and look how the beta band responds, it has the opposite sign, which means this mode in RPA is a demon mode. Doesn't necessarily mean the experiment is a demon, but the mode in the RPA is clearly an out of phase mode between the gamma and beta electrons. The alpha band seems to be a spectator that isn't really participating for some reason. But yeah. They're quasi 1D. There's no symmetry breaking. Go ahead. I think I only have a few minutes left, so I'm gonna, but there's also a question period, right? Okay, so I want to touch on the question of neutrality. This is my first real talk on this, so we'll see how this goes. So as I mentioned earlier, conventional plasmon satisfies the F-sum rule. F-sum rule in 3 dimensions says the integral of chi double prime over all frequencies is proportional to the number of electrons times q squared. So if it's a demon, then it should not do that. It should actually go faster than that because the excitation is neutral. It doesn't screen in limit of low momentum, so it has to violate the F-sum rule. So you could ask, does this excitation violate the F-sum rule? So it's a simple question of asking, what is the intensity of this thing doing as a function of Q? And does it follow what you expect from the F-sum rule, or does it do something faster than that? So there's some subtleties that come up because this is actually we're actually measuring a surface response function. It's not a bulk response function measurement. So we're measuring the chi double prime of the surface. So to understand this, you actually have to derive an F-sum rule for that surface response function. So this is something that Bruno Unchoa at the University of Oklahoma has been working on for about 4 years. And we now have a sum rule. We haven't published it, but it just uses the same techniques as in Nosieras and Pines dating back many years. And this is what the sum rule looks like. There are various ways to express it. You can write a sum rule purely in terms of the response function. You can write the sum rule for the scattering cross section with the matrix elements in there and everything. In this case, we're going to compare to an experiment. So what I'm going to do is focus on the sum rule for the cross section, which looks like this. So this is the doubly differential scattering cross section. This is a Bose factor, so you have to put in the temperature. These are the matrix elements, which you can write down. They're just Coulomb matrix elements. And this is not the electron density, but the surface electron density. So rho of Z is a measure of how the electron density falls to zero as you go from the material into the vacuum. And for small momenta, this is basically a step function. So this whole thing you can simply calculate by hand on a piece of paper. And if we assume that the mode, so we have to compare to something in the experiment. What we're going to compare is the integrated intensity of the mode, in which case you can say, you know, the experimentally observed intensity is some integrated intensity times some just linear dispersion. And if you take this and plug it into this formula, you can show that I naught goes like 1 over q squared. So what that means is that if this gapless mode was a conventional plasmon and it satisfied the F sum rule, meaning I could write down a partial sum rule just for that mode, then it should go like 1 over q squared. And there's matrix elements and things. So it doesn't behave exactly the way you would expect if you measured a simple bulk density correlation function, but it's a well-defined prediction. So if the mode is a demon, then I naught should, in the small momentum limit, should behave like a power law. And that alpha needs to be bigger than -2. If it's bigger than -2, then it is neutral for this kind of measurement for this sum rule. Okay, so here's what it looks like. So this is the integrated intensity of the mode as a function of Q, and this is on a log-log plot because we're interested in a power law. And the first thing you can see is that it doesn't look like a power law at all, which is not surprising. It's not guaranteed to be a power law, but as you go to small momentum, it's possible to ask what power law is it approaching in that limit. I think we have enough data points to at least make a guess. So if you fit that with a line, you get a power law of -1.83. And -1.83 is greater than -2. So based on this, which I have shown in public for the first time, so I'm very interested to hear what I hear, it seems to be consistent with the mode being neutral. So in summary, we've discovered a gapless mode in strontium ruthenate. It's highly reproducible. We saw it in quite a few measurements. My student Ali is extremely confident in this thing, and we think it's a demon. The reason we think it's a demon is two things. First of all, it's gapless. The only way a charge collective mode can be gapless is if it's neutral, at least in the long wavelength limit. And it does in fact appear to be neutral in the sense that it violates the F sum rule in the correct way. So what is a demon? A demon, it's like a plasmon, but what it is it's sort of like a magnon too. A plasmon is a modulation in the density, but a demon is a little bit more like a magnon. It's a modulation in the band index. So in the long wavelength, the overall system remains neutral, but what's modulated is the filling of the different bands. So the alpha band, the beta band and the gamma band oscillate out of phase in such a way that the overall density is neutral, but the filling is modulated. So it's sort of like a spin, it's sort of like a magnon, but it's modulated the band index rather than the spin index. But it's a neutral excitation, so it can stay gapless. And Philip made this picture, which I really like, so I'll put it in at the end. So that's it. Thank you very much.
For questions that we actually had one from Harold Wang online.
Dope silicon along 1,0.
Yeah, so the question is, if RPA works, then any standard metal with 2 components should show a demon mode?
Not true. Okay, I would say any standard metal with 2 components can show a demon mode. I don't think they're required to. For example, if I had 2 baths with very similar plasma frequencies or very similar effective masses or very similar velocities, you might not get one at 0 frequency. They could form an in-phase mode and out-of-phase mode, and such things have been seen in IR. They call them optical plasmons. But it's not a demon unless it goes all the way to 0 and becomes acoustic.
This is a very interesting point.
what is the what experience that you have on two bands? Where you see this.
Yeah. But I think just Harold's hit on a key point. I don't think demons are rare. They should occur in many different materials. So you might ask, well, why don't we see them all the time? The reason is because they don't couple to light. Light measures the long wavelength properties of a material. And a demon is neutral. It doesn't screen. It doesn't show up in epsilon of omega in the long wavelength limit. So you don't couple to it. Also, it sits at zero frequency in the long wavelength limit. So you need some finite wave vector probe that measures the charge response. Right? Neutrons measures the spin response, but you can't measure plasmons with neutron scattering. So it's really something you need eels to measure. But I think there probably exist in a lot of materials.
So maybe I'll read Harold's second comment, and maybe you just answered it. So he says, dope silicon along 100 polarization has pockets in the heavy versus light mass direction.
Yeah.
Question mark. Then in the 111 direction, all pockets are the same. So what happens to the gapless mode? And maybe you're suggesting it hasn't been seen.
Well, I don't think it's been searched for in silicon. The details, issue of directionality is not so trivial because, you know, the question of where are the pockets, that's a statement about K, about the Fermi surface. This is measuring Q, which is particle hole excitations of the excitations across that Fermi surface. So things that, you know, you can have something at Q equals 0 that involves electrons at large momenta, just with equal and opposite Q. So there isn't an easy way to just jump from single particle physics to demon physics, which is sort of the issue Philip is referring to. So you have to do a calculation. What are the general criteria? I don't know.
We have a question over here.
I'm just curious, is it possible to also have this between an electron and a hole band with both of them in phase?
Yeah, absolutely. Yeah. I think whether it's electrons or as long as there's a band crossing the Fermi energy, it's a candidate. I think Blaise.
So if I understood correctly, this word that you take is hybridization of transport modes with distinct transport frequencies, efficiently distinct.
Yeah, yeah.
So my question, I think you said it, but do you see the partner mode?
Yes. Yeah, the conventional plasmon.
So the one that
Yeah.
sits at the sum of the two frequencies.
Yeah, that's the thing up at 1.2 eV that I showed you first. This thing. That's the in phase mode.
Can you then track those trajectories and see if they collide or something like that?
Yes, and then what that does is that what happens is the many body physics kicks in and just prevents you from doing that. So if you look at the, I could show it here. So you can see that as you increase Q, this thing starts to Landau damp because there's more electron hole pairs it can decay into at finite momentum. So its width gets broader as a function of Q, and then at some point at around 0.08 reciprocal lattice units, you just lose it because it just decays into it. What's that?
Do you have the other mode of that mode?
Which this one? Yeah, this is it. So the low energy one decays by about 0.08 reciprocal lattice units. The high energy one, maybe 0.16 to 0.2, it's gone. It turns into this marginal Fermi liquid looking stuff. I don't know what the politically correct term is for continuum now, but I call it marginal Fermi liquid until there's another name. But they never meet because they both damp before they get there.
Does the demon help at all to understand why that apparent strange metal from high energy or temperature disappears?
It doesn't help me, no. It might help some smarter people than me.
Wondering, so does this demon mode when you cool it, is it the mode towards called the Leggett mode?
Oh, I would kill to be able to see a Leggett mode. Let me tell you, it's temperature dependent. If you want to get into that, if you want to go down that rabbit hole, the velocity changes with temperature. So as you cool the system, okay, I've got way too many backup slides, but as you cool the system from the room temperature, strange-ish metal regime down into the Fermi liquid regime, the velocity renormalizes by about 15–20%. So this thing is decaying into a particle hole continuum that's some incoherent continuum, and that continuum sort of derives from all the strange metal physics. And that's reorganizing with temperature as you go from the Fermi liquid regime to high temperature. And this mode feels it through the Landau damping into that continuum. I can't. I don't have good enough resolution for that. What's that? It's a lot like you raised the Leggett mode is the out of phase collective plasmon mode in a superconductor, and it is the analog in a normal metal. But it's the same mode, just of the normal electrons. So you can say, does this turn into the Leggett mode when I go through TC? I never thought about that. Maybe.
My question was actually about the velocity. Just make sure. So this things like second sound, you completely eliminated the possibility that there is some mixture of second sound to plasma.
Second sound was Landau's name for a plasmon, if I remember. Or did he call it first sound?
You say that there are temperature dependencies.
Yeah.
Where it's second sound would mix with the actual plasmon, especially system has a low carrier concentration. There will be a non-vital dependent on Q. So my questions are, is this something or a picture? Can I follow? Do you know anything about like width and attenuation of this mode?
Yeah, there's the width. I'm gonna, on the question of first sound versus second sound, let me just take the fifth on that. Here's the width. So this follows a nice power law as well. And this is Landau damping. So there's a continuum, it decays into the continuum, and we can measure that too.
So I was staring at your dispersion. The color plot seems to also have some information about intensity.
Yeah.
This is energy.
Yes.
And does that say something?
Yes, that is exactly what is shown here. That's this. So this is the key point. This sum rule sets constraints on what the intensity of the mode should do with Q. And in a normal metal, the plasmon, the intensity is always Q squared. And in this, it does something else.
It's increasing as Q decreases.
The spectrum, the weight, the
Wait.
integrated intensity decreases with increasing Q, but that's because the matrix elements are Q dependent and they decrease. So
Is that expected? So like if I have spin waves, I know what the intensity,
yeah,
which is only I should behave like.
yeah,
Is there expectation of
it should be -2, but it's higher than that, which is what you'd expect if it's a neutral mode.
Okay, one last question and we'll go to the next. Did you check that for actual plasma that it's exactly -2?
I've done it many times. I should show you data from graphite. We verified Q squared over 3 decades in that material. So I'd be delighted to show you lots of old data during coffee break, if you'd like to see it.
And on that note, let's say, for the next talk. We're about 10 minutes behind, so should we meet here in 15 minutes and have to split the difference?
Yeah, make interesting.
Hi, Harold.
Thanks for letting me ask.
You know, you could have asked, we can hear your voice in the conference.
Oh, okay. That's not maybe a good thing. Anyway, just wanted to say hello.
Hi, Harold.
Hey. Okay, so 15 past 6.
Thanks.
Question for you. The richest electron doping, is that moving the right bands for the Steeman thing?
Oh, so you're talking about if I put calcium in it or something, or lanthanum. Oh, goodness, I never thought about it. What happens to the bands? In that,
Well, in principle,
there's a
quantum critical point.
Yeah, where the Fermi surface changes topology, right?
Yeah,
Yeah, which bands are the ones that break?
yeah, right. I think it was the gamma band. I'm not 100% sure.
Then this thing should do something highly non-trivial. Yeah, that's actually a good idea.
So we've been working a bit on trying to explore sort of this Lipschitz transition a different way via iridium alloy against the ruthenate.
Yeah,
So basically on the transition.
in strontium ruthenate.
It's not ruthenate.
Really?
You can access the same type of quantum critical point as with lanthanum doping, but there's a spin degree.
You're not Stephen Wilson.
Yeah, I'm Stephen
Okay,
Wilson.
okay, good. I've never met you. I just know your name.
Just via Zoom, right?
Yeah,
And then it's impossible with math.
yeah. I
Sorry.
was just guessing based on the growth, who it had to be, but
Yeah, sorry, I should have.
I see. So you've actually grown lanthanum dope strontium ruthenate, and there's a
Yes.
Fermi surface
Yeah, yeah.
transition.
We focus mainly on the iridium dope starting ruthenate.
Yeah.
We want to do the whole phase diagram. So.
Yeah, does that do something intriguing?
Yeah, it does. I can show you some point. It does interesting things like like so strontium ruthenate, right? Basically has no at low temperature has no local moment. It's very small.
Right.
So basically, across this kind of critical point, basically local moment just explodes up, and then you get sort of like strange metal transport.
Yeah.
Strange things.
Really?
Yeah, it's a funky.
Send us some samples and we'll get to work.
Yeah, I mean,
We'll have to turn this off.
okay. Yeah.
Yeah, we're always
I can show
looking
you some of
for.
the stuff maybe other time and something breaks here.
Is it working now? Or-
Oh,
Yeah. There's some button on
okay, okay.
there, right? Yeah. Okay. Yeah. So non-Fermi liquids in translationally invariant systems, they have Fermi surfaces, but no quasi-particle excitations. And possible scenario to achieve non-Fermi liquid behavior is a couple of a Fermi surface of electrons to fluctuating quantum critical bosonic mode, like say a ferromagnet or an emergent gauge field, especially in two spatial dimensions where the fluctuations of the phi are strong. And like once you couple your fermions to this phi, if you just do field theory at the one loop level, these bosonic modes get damped, and that leads to a large self energy for the fermions. And the point is that the energy dependence of the fermion scattering rate is parametrically much larger than just the excitation energy omega of the fermions as well. So even if the prefactor of the diagram leading to the scattering is small, since you have a parametrically larger quantity, it always dominates at low energies, and that prevents a weak coupling expansion in the fermion boson coupling. So to come up with some field theory method of being able to self-consistently solve such a problem at strong coupling, what much of my work has focused on is to exploit features of the SYK model. The SYK model is a model of a non-Fermi liquid, but it's only in 0 spatial dimensions. So it consists of a large number of fermions with all-to-all random interactions. And because of the randomness in the interactions, if you look, there's an exact relationship which resums to infinite order in J, a certain class of diagrams that gives a relationship between the self energy and the Green's function. And that the solution of those Schwinger-Dyson equations leads to a Green's function that is a power law form at low energies, and it doesn't have a delta function spectral peak that you would expect with quasi-particles. So since the routes towards non-Fermi liquids that I was talking about are not in 0 dimensions, and they also involve fermions coupling to bosons, what me and others also did was to you can also have an SYK-like approach, but have random interactions between fermions and bosons. So there were various works, starting with case where we considered the bosons to be gauge fields, but then there were others who did it with scalars and many other different versions with various other features. And these are all in zero dimensions, just like the original SYK model with a large n number of fermions and bosons. And they do lead to, just like in SYK, they do lead to exact equations between the Green's functions and self energies, except there are now a boson self energy and a fermion self energy. So you get these kind of RPA Schwinger-Dyson equations. So to apply this to something that's beyond 0 dimensions is fairly straightforward. All that you have to do is keep the dispersions of the fermions and the bosons in your 2-dimensional theory, but promote both fermions and bosons to have large n flavors at every site. And then again, use the same kind of random coupling between fermions and bosons. And in the large n limit, this gives you an exact set of RPA Schwinger-Dyson equations. And just in this, and just like in SYK, even here, we take the large n limit before the low energy limit in order to be able to solve the problem. So yeah, as I said, the large n, this kind of large n construction in 2+1 dimensions, it gives these exact Elie-Ashberg equations with resum
all diagrams to all orders in G within a certain set. So they are strong coupling equations. And now what happens is you can solve these exactly in the large N limit. And when the boson's critical, where you tune its mass to 0, they have a non-Fermi liquid solution where the fermion self-energy of omega to the 2/3 dominates. And within this construction, where you take the large N limit before the low energy limit, it's all controlled. Okay, so this tells you how to develop controlled field theory for translationally invariant non-Fermi liquid. But to get transport properties and strange metal behaviors, translationally invariant theories have a problem that they have conserved momentum and current. At finite density, there's overlap between the current and momentum. To relax current, you have to relax the momentum, and therefore you have to do something to relax momentum, like have some weak Umklapp process on a lattice or have disorder in the problem. And so we have to build that into these models of controlled field theories for non-Fermi liquid critical points. So one phenomenological construction that has existed for a long time is a marginal Fermi liquid, where if the bosonic susceptibility has this local form, it doesn't depend on space, but only depends on time or frequency, with the log singularity that gives a single particle electron scattering rate that's proportional to temperature at a finite temperature. But this of course is not the transport scattering rate, it's the one particle decay rate. And one has to come up with some way to derive this systematically in some field theory. So, but however, it's a nice ansatz. There is actually experimental evidence for marginal Fermi liquid self-energy from ARPES, like in this pnictide material, where the self-energy is proportional to the frequency. It's a constant plus something proportional to the frequency. So the key to getting some relaxation of momentum and therefore finite resistivity will be to that I will pursue will be to include the effects of disorder in order to relax currents. So one can just take the quantum critical theory, and the first way to add disorder would just to be adding a random potential term to the quantum critical theory, which is written down this way with the large N SYK-like construction. And if you include such a term, this modifies the low energy behavior of the fermions, which leads to a boson propagator at the critical point that has this diffusive form. And then the correction to the self-energy that the fermions get from scattering off the boson is marginal Fermi liquid-like. That comes in addition to residual impurity scattering of the fermions. However, because the fermion boson interactions are dominated by Q equals 0 bosons, it's largely forward scattering and no current is relaxed. So there's no T-linear correction to the resistivity, which remains a constant at low temperatures. So to get T-linear behavior, we consider the possibility of having disordered interactions. So where in addition to the potential disorder, we can consider the disorder occurring in the interaction coupling between fermions and bosons. So you have a uniform G and a G prime that is disordered and random in space. Now, again, when you do this, you end up with a boson propagator that's the same form and a marginal Fermi liquid fermion self-energy. But now there is an interaction between the fermions and the bosons that because it's spatially random, it's no longer forward scattering. It can scatter by large amounts of momentum because it breaks translational invariance. And that relaxes both current and momentum and gives you a T-linear contribution to the resistivity. So resistivity is now constant plus T-linear, and the slope of the T-linear correction derives from a different parameter, G prime, whereas the slope of the, whereas the intercept residual resistivity derives from this parameter V. So there are two independent parameters. And one can also eliminate the V term and consider only disordered interactions of this kind. And then because you still have this clean part that dominates the fermion self-energy, you get omega to the 2/3 fermion self-energy. But the disordered interaction leads to a marginal Fermi liquid correction to this omega to the 2/3. And since the omega to the 2/3 comes from forward scattering, but the correction does not, when you look at the transport properties in this theory and sum up all the vertex corrections in the large N limit, there is no T to the 2/3 resistivity. Rather, your resistivity just comes from marginal Fermi liquid correction, and you get a T linear resistivity. And because there's no, the disorder is coupling to higher order interaction operator and not the potential operator, there's no residual resistivity, even though this is disordered within the large N limit. Okay. Then, yeah, I mean, strange metals also tend to have this feature of Planckian dissipation, where if you're doing DC transport and trying to use the Drude formula, knowing the density of carriers, if you use appropriate effective mass that includes effects of interactions, you get a scattering rate that is order 1 number times kVd over h bar. So one can also derive this from these kind of control models. And the trick is to consider fully disordered interactions. So I'd like you to focus on this term here. The fully disordered interaction means there's only G prime now, no G. So the interaction is completely just random in space. And then the other terms describe boson self-interactions and stuff that are also important for solving this thing properly at finite temperatures. You can tune it to a critical point, and what one gets within the large N framework is a scattering rate that's T log T, and that also represents a transport scattering rate, and giving nearly T linear resistivity with a log correction. But the nice thing here is you had only one interaction coupling that's fully random, which was G prime. So when you look at the renormalization of the effective mass, that is the single particle self-energy, doesn't have to do with transport. It's only G prime that contributes. There's no any kind of additional interaction contributing it. So you have the same interaction contributing both to transport and to mass renormalization. So when you define tau star in terms of m star, the interaction cancels and one gets kVd over h bar times some order 1 number times some logs, which contain all the non-universal stuff. So all the non-universal stuff is, it's depending on how you want to cut things off. All the non-universal stuff is shoved into the slowly varying log functions. So one gets nearly kVd over h bar times some order 1 number. It doesn't differ by, you don't get 10 kVd over h bar and 100 kVd over h bar, even though the non-universal stuff can be very different in different materials because it's within the log. And for this, the fully random interactions are important. Okay, how am I doing on time? Okay, right. So quickly, I'll also try to describe, like, there are many strange metals which have only a single slope of resistivity over very large temperature range. That hints at some kind of scale invariance. So we can derive that. We can actually show that there is a scale invariance just by looking at the Kubo formula. Rewriting of the Kubo formula leads to where I is the current operator and Z is the partition function, leads to this quantity f of E. And if this f of E quantity, which is defined in the microcanonical ensemble, is completely independent of the energy scale, one gets exact T linear resistivity. So that motivates a connection or an exact mathematical connection between single slope resistivity and this and the energy scale in the microcanonical ensemble. But I guess I'm out of time now, so I will kill the talk. Right. Right. That's the conclusion.
Don't worry.
Okay, well, thank you.
Is it true that this nearly universal slope happens in the vector, meaning that then G squared is larger than 1?
Yes. Yeah. Yeah.
What happens to your Planckian behavior when you turn on this G and have G as well as G prime?
It's not Planckian anymore because
How does it change?
the effective mass renormalization now depends both on G and G prime, whereas the transfer only depends on G prime. So you get KBT over H bar times some ratio of G prime over G plus G prime or something like that.
Is there a Matthiessen's rule for the usual potential disorder and this kind of scattering? Do they just sum?
Yeah, in the large ends model, it is a Matthiessen's rule. Yes.
Time for one more question. Yeah, go ahead. I don't remember if I've asked you this before, but in your last the Symbolian
Yeah.
thing, for many situations, what you have is the system that is constant.
Right. Yeah. So I think the
incorporate that into, is there a statement that allows for a constant?
I haven't found one despite trying yet, but I think that's an important point, and probably this perfect linear resistivity strange metals are different from the ones which are constant plus T linear.
The real perfect ones, if you disorder them, they do develop residual resistance.
Yeah.
So because formulating something does the conductivity, so it's 1 over T times
Right.
something big.
Yeah.
And then 1 over T has to become 1 over T plus 1.
Right. So I don't know how to fix that. Yeah.
Can you comment if it's possible to break the transition in various way out and crop the scattering in your model without disorder?
I mean, put it on a lattice and get umklap. Yeah, that doesn't give a T linear correction if you try that with the.
Looked at by one last question.
What's the upper limit in temperature where this theory is applicable? I mean, can you conjecture that it can be applicable to very high temperatures?
So if you go to high enough temperature, but keep the large N construction exact, what eventually happens is your self energy becomes so large that it exceeds the bandwidth, and then you go into this locally critical regime. So there is a scale for that happens, and then it's not T linear unless you do some fine tuning and other stuff. It's all T less than the order bandwidth than bandwidth. But it's still pretty large in terms of the other scales.
How about low temperatures?
No, not in the large N constructions. You can get T linear all the way down to low temperatures. Yeah. Zero.
Thank you for your talk.
Yeah.
Does that work better?
Yes.
Okay. Okay, I will talk about pseudo gap formation due to magnetic fluctuations at finite temperature. First, let me thank my collaborators. This talk is based on these two works in collaboration with Andrei Trubakov, Zhentao Wang, and Rafael Fernandez from University of Minnesota. Yeah, the formation of pseudo gap has been one of the most debated topic in the study of high temperature conductors. In this schematic phase diagram, we can see that the pseudo gap span over a wide range of temperature and doping. So there have been two case scenarios to understand the origin of the pseudo gap. One is that it is a new phase with some order, and we have heard a wonderful talk by Subir today. And another scenario is to regard it as a precursor of a vestigial state due to some local order parameter, more conventional ones such as superconductivity and magnetism. So in this talk, I will consider the magnetic fluctuation mechanism and see how far we can go. And there have been indeed supportive evidence for the fluctuations in the pseudo gap formation. So one important evidence is from this numerical studies using the DMFT, where from this left panel plot, you can see that the speed fluctuations is a dominant fluctuation channel. And to be specific, it is an antiferromagnetic fluctuation. And from this right panel, you can see that this static fluctuation dominate. So for this reason, I will consider the effect of the static antiferromagnetic fluctuations. I should also mention that I'm not going to talk about anything at zero temperature, and I will, as a result, I will ignore the, this is also another reason we can ignore these dynamical fluctuations. And also it turns out that if we consider the magnetic fluctuations, just a dynamical fluctuation is not enough to induce any pseudo gap. However, if we only consider the static magnetic fluctuations at finite temperature, we can indeed find a way to introduce the pseudo gap. And also, it is an analytically controlled calculation, so we can do a quantitative study in a great detail. And there are also other evidence for the magnetic fluctuations from well-known experiments back to like 2 decades ago. Okay, so now let me tell you a bit more about what motivated us for this current study. So one motivation is from the recent numerical study on the 2-dimensional hybrid model on the square lattice, such as the DMFT and the diagrammatic Monte Carlo at intermediate coupling, where they find a new quantitative, they give us new quantitative understandings. And let me quickly review what the findings there. So first, it can be shown that the pseudo gap scale is proportional to temperature times log of the spin correlation length. And we can easily understand this energy scale by just considering Fermi liquid interacting with some static magnetic fluctuations at the second order perturbation. However, the question is what determines this magnetic correlation length, spin correlation length? And if we, to be consistent, consider this Fermi liquid picture within second order, it turns out that the spin correlation length is a constant. And however, the DMFT study shows that the spin correlation length is proportional to exponential of inverse temperature, which is a feature that can be captured by the nonlinear sigma model if we consider a localized spin model. So, however, as I mentioned, we are considering this Fermi liquid interacting with the magnetic fluctuations. So the question is, can we start from this Fermi liquid and get this spin correlation length that can be captured by the nonlinear sigma model? And this set our motivation for this study. And the resolution is that we can go beyond the second order perturbation and instead consider an infinite series in the diagrammatic calculation. And we indeed find that the spin correlation length could be kept exhibit this exponential behavior. Okay, so and I will tell you more about detail in the rest of the talk. And another motivation is from the current experimental progress to simulate the Hubbard model on other lattices. For example, the triangular lattice Hubbard model, which can be potentially simulated by the TMD Mori heterostructures. So it's interesting to see whether these procedures can be applied to other lattices with different kinds of magnetic order and what is the features there. Okay, so to begin, let me first tell you about what we would expect from a simple mean field picture. So let's start with let's start at high temperature, where this right panel shows the Fermi surface in this blue curve. And as temperature decreases, the system starts to develop spin density wave at momentum q equals to pi pi. And we can see that this tendency by looking at the spectral function at these hot spots, where in the Fermi liquid side, it's peaked at 0 frequency. And as soon as the order starts to develop, the spectral function is gapped at these hot spots, where this gap is determined by the SDW order parameter. However, this simple mean field picture is not what was observed in the experiments. Instead, near the nil temperature, we will be able to see a finite energy maximum, namely the pseudo gap, even though the SDW order vanishes. And this is the feature we want to understand. Now let me go through the qualitative findings from our results by walking you through the evolution of the spectral function as temperature varies. So at low temperature, deep in the SDW ordered state, the spectral function looks like the mean field picture, which is peaked at the finite energy determined by the SDW order parameter. And as the temperature increases, the SDW peak shrinks. And in the meantime, there is another hump feature appears. And as the temperature further increases above the nil temperature, we see that there is no SDW gap, but this hump feature remains all the way to a much higher temperature. Then the system recovers to the normal Fermi liquid-like behavior. And from this evolution, we can say that there are 3 energy scales evolved here: the SDW order, the hump energy, as well as this fermion energy that determined the width in the Fermi liquid side. And I will now next explain how these 3 energy scales interplay as temperature varies. And furthermore, I will explain to you what are these physics that mimic the localized spin model from this calculation. Okay, so let me next quickly explain what is a computational procedure. So the idea here is that as we consider the magnetic thermal fluctuations, we know that there will be some logarithmically divergent piece, which is essentially the same part that destroys the long-range order in 2 dimensions. And in our calculation, we only keep those logarithmically divergent parts, which turns out need to be kept to all orders. So we need to develop a non-perturbative diagrammatic summation to treat those logarithmic order diagrams. And because of the logarithmic divergence, below the nil temperature, we will cut off by introducing 2 plus epsilon dimension. And above the nil temperature, it can be naturally cut off by the spin gap, which is proportional to inverse the spin correlation length. And next, we can write down the self-consistency equation below the nil temperature for the SDW order and above the nil temperature for the spin correlation length. And we also keep the chemical potential in our calculation. And schematically, these are the diagrams we need to consider. I will not explain why, but just want to emphasize that this is not any RPA or Aavishkar-like summation. But it can be done accurately here because when we only consider the static fluctuations. And now, in this calculation, the full Fermi surface. Yeah, but the spin fluctuation is close to Q equals to pi. Okay, now let me explain in detail how these 3 energy scales evolve. Let's see what happens when U is about 1 electron volt in the intermediate coupling regime. And from this plot, you can see that at very low temperature in this red shaded area, the SDW order in green is the largest energy, so that correspond to this SDW gap in the spectral function. And as temperature increases, the half energy start to emerge and becomes bigger than the SDW gap. And that's why we can see the 2 peak feature in the spectral function. And about the nil temperature in this in this green region, we see that the SDW gap vanishes, but this hump energy remains relatively constant, and it disappears only when the fermion energy becomes larger than the hump energy in this blue shaded region, and we will see the Fermi liquid-like behavior. And let me next say how these 3 energies change as we vary the coupling, the Hubbard U. And for weak coupling, we don't see any SDW order and also no pseudo gap. And at stronger, from intermediate to stronger coupling, we see qualitatively the same thing. The only difference is the pseudo gap region becomes broader as we increase the Hubbard U. And we can also look carefully how the spin correlation length behaves as a function of temperature. And we find that this spin correlation length scales exponentially with inverse temperature, as you can see here. And for comparison, I also show the result from the DMFT studies. And this straight curve essentially means it is exponential behavior in the log plot. And let me emphasize again that this is purely from a Fermi liquid treatment, but because we go beyond the 2nd order perturbation to all orders, we are able to capture this physics. And also because of this behavior of the spin correlation length, this hump scale remains a constant about the nil temperature, as you can see here. And we can also generalize this whole procedure to other magnetic order, for example, the one without the non-collinear order. And the key difference, for example, on the triangular lattice is that because it's coplanar, there are 2 types of low energy magna modes, the ghost modes. One is associated with the in-plane fluctuation, and another is the out-of-plane fluctuation. And their susceptibility can be different. And because of this difference, the hump energy changes from this collinear order behavior to another one where it is proportional to some in the power law behavior to Z over 1, where this Z is determined by the ratio of the 2 spin susceptibilities. And so which can vary from 1 to infinity. And then because of this, we can get the phase diagram as a function of as the z varies. And I want to emphasize here that following the same procedure, we find that when z equals to 1, there is no pseudo gap behavior. And by varying the z, we can vary the range of the temperature range for this pseudo gap physics. And okay, yeah, that summarizes my talk. And I introduced and studied a minimal analytical model to capture the formation of the pseudo gap behavior quantitatively. And we also compare with the DMFT studies, which are so far carried out only at 0 doping. And it would also be interesting to look at how these pictures can be help us understand the transport properties. And also it would be interesting to think about the ways to tune this Z in the experimental platforms. Thank you.
I'll start. So I missed how you said that you did these calculations in a controlled way, and then you showed results for large U. How did you control those calculations for large U limit?
Oh yeah, so there is no there is no like small parameters in this problem. So the way we control it is we keep all the logarithmically divergent diagrams that gives us a series, and we can sum up these diagrams. And all other diagrams that have regular contributions will be like suppressed.
So you carried out the calculations only for 0 doping, or you have a doping dependence too. So yes, what's the doping dependence?
Yeah, we considered other dopings as well, so schematically we didn't find a big difference by varying doping and 1/U within our procedure. Yeah, but when we question the validity of only considering spin fluctuations when one changes the doping a lot.
I have one additional question as well. So was spin rotational variance very important in your calculation? And do you think if you add spin orbit coupling, the results will change to some degree?
I think very schematically, varying the spin orbit coupling essentially will gap out some of the ghost modes. And if they are still weak and we can still keep them, just they becomes a little bit massive, it's similar to tuning somehow tuning this Z factor. Yeah, so there is a way to do that, but for the triangular lattice, I think that is one way to actually tune this Z effectively. And for the square lattice, we need to like think more like how effectively what is a diagrammatic series. So that kind of change some kinetic condition in the diagrammatic summation.
Any additional questions? Okay, if not, thank you again.
Thank you.
I missed a question in the chat in the last talk, and so I don't know, this was Dominic was asking the question. Perhaps he can re-ask it. I'm yelling because maybe he can hear me then.
Sorry, that was a question about if you can hear me, that was a question about the previous talk actually.